Here we look at the Quine-McCluskey method, which is a tabular method to do our Boolean expression reduction. So we want to simplify. Remember before we looked at the Carnot maps, the K-maps, we used them to visualize how a group of our terms in an expression would simplify. So we could see that, how they're going to simplify. But after, say, 4 variables, it's hard to use the Carnot map. So we might want to use this tabular method, which is a little tedious, but it is systematic. The order in a K-map was such that each cell, which was the adjacent values, differed only by 1 bit change. So here what we're going to do is we're going to actually search for the terms. So instead of looking at it to see how they're going to simplify, we're actually going to search the terms in a table to group which ones we should be grouping together. So we're not going to have our blocks, our groupings like we did in the K-map. We're going to be searching to group terms 2 at a time. And well, if we can group more than 2 at a time, that'll be fine. But we would still want to group them such that we have 2 grouped or 4 grouped or 8 powers of 2. So the min terms in the given expression are first going to be represented by bit strings. So that's how we're going to put this in the table. There are 2 main steps. We're going to determine which terms will be candidates to include in the minimal expansion, and then from there we'll determine which ones to use. So this is the Quine-McCluskey approach. You want to create a bit string for each term. So for each variable in a term, we're going to represent it with a 1. And for each variable's complement, we're going to represent it with a 0. So that way we'll be able to see where we have a change from the variable to its complement. And we're going to make sure that we have a complete sum of products. And we're going to have, say, if we had x, y, z, we can have complements there wherever we would need. But we want to make sure that we'll put all the x's here for the bit, and then the y's, and then the z's. So we'll keep that order, but it could be a complement if we put a 0 down. We're going to organize the bit strings in a table, then count the number of 1s in each term's bit string. So we do have to do this first. We're going to look at the number of 1s in each term's bit string so that we can put the bit strings with the most 1s on top, and then the next most 1s, and then the next. So we do this since we know min terms that differ by exactly 1 literal can be combined to just 1 product of literals. So their bit string representations here must differ by exactly 1 in the number of 1s. Okay, so that just means we want to look at if we had 1, 0, 1, it has to differ by just 1 bit. So maybe this one. Then we would be able to combine. Okay, so we'll look at that. We're going to use a dash to denote the variable that does not occur. That means the one that's eliminated, the one that's reduced out, simplified out when you combine, when you add the terms together. So we'll just use a little dash to represent that. Continue to combine the terms into 2 literals, and then combine your pairs into 1 literal there. And here's an example of using the Quine-McCluskey method to find the minimal expansion that's equivalent to this given output. So notice the given output is in the complete sum of products form. It's in that disjunctive normal form where each term has the variable x, y, as well as z, or its complement. And that's important to us because we're going to be comparing bit strings, and we need to compare bit strings of the same length. So we want to make sure that it is in the complete sum of products form to start with. What we're going to do is represent each term as a bit string and put terms with the most 1s on top of our table. So if it has the variable, we're going to put down a 1. If it's the complement, we're going to write down 0. So x, y, z is just 1, 1, 1. A complement for the next term becomes 0. Y complement, z complement. Then x is a 1, y complement 0, z is a 1. X complement is a 0, y complement is a 0, z is a 1, x complement will be a 0, y and z will be 1s. So that's what I've written down, are all their bit string representations with 1s and 0s. And the next thing we do is we need to count the number of 1s. So let me just count the number of 1s here. So I have 3 1s, 0 1s, 2, 1, as well as last one has 2. So I want to put them in the order of the most number of 1s to the least. So the first term would be x, y, z at the top of my table. And then the next will be the one with 2. So now I have this one as well as this one, so it doesn't matter which one I put next, but I'm going to put those next. Then 1, and then the one with 0 1s goes last. Okay, so I filled out my table here, and I'm going to number. So I'm going to number each of those terms. So I started with 5 terms in the complete sum of products form, so I'm going to number them from 1 to 5. But again, the order is the most number of bit strings on top, then the least on the bottom. The next thing that you do is that you're going to be adding these terms. So I put down this column here that says add, but what we're going to be doing in a table is we're going to be comparing. So I know with the K-map we were able to visually see how to cover our 1s to get with the prime implicants, but what I need to do now is just compare the bit strings. But let's show you what's happening. So I look and I say, well, this first one, bit string, differs in only 1 bit with, say, 2 or 3. So if you notice, where do they differ? So this differs here between 1 and 2. So you were taking these terms, and the table says if you add them, so if I add these terms, you can factor out xz, which is in common. So that means use the distributive property. Then the terms that were opposite, y plus y complement, are going to eliminate out to a 1, so that your end product is xz. So you've gone from 3 terms to just 2. So by combining or adding the first and the second terms, your result is xz. And how would you write that as a string? The string would be, this is important as well, as we wrote our complete sum of products form, I put the x's first. So notice we put all the x's or its complement first, then all the y's or its complement, then all the z's or its complement. So in that first bit, that represents x or the complement. So I have an x, so that means I'll be writing down a 1. Now is there a y? No, that was eliminated out, so we put a dash. And then I have z, so that's a 1. So this is the string representation from adding 1 with 2. So we don't do this in general because that's long. Now in a K-map you could visualize how to do that, but when you get higher than 4 variables, it's hard to visualize with a K-map. So this is going to be nice. It is tedious, but this will be a nice systematic way to simplify. So what I could do is I also have this column called compare, because we need to compare the bit strings. So I take the first and the second and I just compare them. Okay, I'm comparing them. So where do they differ? They differ in this bit, and you know that corresponds with the y as we have it listed here. So the x is going to stay x, so the 1 is going to stay because that's the x is going to stay. The y's, as we saw before, they get added out, so we put a dash. They're eliminated, and then the z stays. So we keep it 1 dash 1, so you get that same string back here. And then when you write the term will be x because it's a 1, the y you don't write because it's eliminated, and then the z. Okay, so that's how I work these out. So you just go down the list, start with the first. We did the first and the second and keep track. So you were adding the first and the second to get this new string. But just think about comparing the bit strings. Next, if I look at the first and the third, see they differ in just that first bit. So I compare them, the first with the third. So here you're looking at the first with the third compared. They differ here, so if you were to look at those terms and use Boolean identities, then you'll see that the x's are going to add out. You'll get x plus x complement, and then when you multiply that by the yz, you'll be just left with yz. So this part is going to eliminate out, and we're going to be left with, so this implies our result will be eliminate the x, then you'll have the y, and you'll have the z left. So this is our new string. If you write that as a term, it's going to be just yz. And that was using 1 together with 3. Okay, keep going down. Can you compare 1 with any other bit string? Now we're not going to be able to do that. So if you notice the 1, 1, 1, and if I looked down to 4, they differ in 2 bits. So that's not going to work. And I knew that because this had 3 ones, and this has only had 1. That only has 1 1. So there's no way that it's going to differ in just 1 bit. It'd have to have 3 1s or 2 1s in that case. So we move on. This one's done. So now we move on to comparing 2. So I look at 2. What can I compare 2 with? Well, not 3, because that differs in 2 bits here, but I can compare it with 4. So if I look at 2 with 4, I'm going to write down the bit string. And where does it differ? It differs only in the first bit, so that means the x is going to get eliminated. So we write the dash. Then you keep the 0 and you keep the 1. So that means if you were to use the Boolean identities, you would end up with not an x. The 0 means y complement, and the 1 means z in that position. So you would end up using 2 and 4. This is what you have. Okay, so let's see if is there anything else for 2 to be compared with. So 2 is done. Okay, so 2 cannot be compared here with 5 because it differs in 2 positions. So I'm going to cross out that we're done with the 2. Now you look at 3. So you look at 3, and that differs in only 1 position here with 4. So I am going to use 3. So you're keeping track. And I have this listed on the table, but I'm using 3 and 4 to compare. They differ here in the middle, which means the y's are going to add out. You'll get a y plus a y complement, but you'll end with the product of a 0, 1. But notice the 1 that's eliminated, so that we can compare at the same length, we need to put a dash there. But that means that 0 is going to be the complement. The y I don't write in my term because it's eliminated out, but the 1 represents z. So this is what I've written down here. Okay. And finally, 4 with 5. Okay, so we're down to the last part here where I'm going to now compare 4 with 5. So I take 4, 5, compare them, and 5 is all zeros. They differ on the last bit, so this one is going to eliminate out. So I'm going to keep 0, and a dash for the variable that's eliminated. And what would that mean for your term? So how would you write that term? It would be, first position means an x, but it's a 0, so it's x complement. Then the 0 in the next is y complement. And then I don't write z because z is eliminated out. But this would be the string representation. This is the term. Okay, so we're done adding those two at a time from the first right-hand side of my table. So now I'm working with this middle part. Now in the middle part, you want to add 2 of those at a time as well. So I have to match up, though, the dashes. So the dashes are going to need to match up. So you might want to look to say, where do those dashes match up? And I see they only match up with the 1, 2. See, now I'm going to use this notation here, the 1, 2. That used 1 and 2 to get to this result. and this used 3 and 4 to get to this result. So when I write this down, I'm just saying I'm using the 1, 2 result, and I put a semicolon here just to represent that, and then the next one is 3, 4. So if I looked at that, I'm going to compare their bit strings. That's the 1, 2, and then 3, 4. So I am lining up this. So that has to line up, and then they can differ at most at one spot. So yes, they differ at most one here. So that's going to eliminate out. Then I have my dash that drops down, and then the 1. So how would you write that as a term? The x's eliminate out, the y's eliminate out, so you're left with just 1 in the z. So you get back z. So we wrote the term z here, and it's string representation. And if you're not sure, if that's true, then you can just look at, if I am going to add those together, you really would get back z. So let me just show you. If I took this term and this term, so there's lots of verifications you can do. You can definitely see that you're going to get the z back by using the Boolean algebra. Okay, but we're supposed to avoid that since we are using our nice table with 0 and 1 representations. So what's the next step? So the next step is, I'm down here and I have z. Z used 1, 2, 3, 4. We're keeping track as we were going. So that used all of those. So this is a candidate for my simplified form. It used 1, 2, 3, and 4, and it was able to simplify down to z. So the z candidate used 1, 2, 3, 4, but it did not use 5. So it did not use min-term 5. So what I have to do is I have to account for that one by looking over. Now, as I was going from one step to the next step, notice that we were leaving off some information. We're just leaving it behind. So I don't come back to this part of the table when I was, once I finished this part. This is the part I'm going to work on with now. So this did not use 5. So if you look, anything that has 1, 2, 3, 4 in it is already accounted for. So it has to have the 1 and a 2, or a 1 and a 3, or 1 and a 4, any combination together. So this one is already accounted for. The 1, 3 is accounted for. The 2, 4 is accounted for. The 3, 4 is also accounted for. But the 4, 5 is not accounted for because of 5. This did not use 5. So what I have to do is I have to take this one as a candidate as well. So my candidates become the z and the x complement, y complement. Now we'll have to put those in a table as the rows to figure out, do I take both of them as my simplification, or am I able to just use one of those? And you'll see that you'll need to have both. Okay, so I put my candidates here in the rows for my simplification. Now at this point, in the columns, you put down each of the original terms, each of the min terms. Remember our sum of products that we started with, the complete sum of products? I want to make sure that each of those terms are used in this simplification of z down to z and x complement, y complement. So place an x in the entry of the table if the original term was used to form that product that listed, that candidate. So the candidate, you can just call it a candidate. So which one did z use again? So remember, z used 1, 2, 3, 4. Used all of these, 1, 2, 3, 4. So I'm going to put 1, 2, 3, 4 were used to get to z. Now what was used for x complement, y complement? To get to x complement, y complement, 4 and 5 were used to get to that point. So I'm going to do 4, 5. See, I've labeled them up here so you can see. So which ones do I use? Do I just use the whole thing simplifies to z, the whole thing simplifies to x complement, y complement, or do I take both of them and add them? Well, if there's only one x in a column, then we have to include that product corresponding to the row. The product just meaning the candidate. I just like to call it candidate. So if there is more than one x, then either term can be used. But notice there is one, for this one, for example, it only has an x here. It doesn't have an x in both places. So right away, just because there's only one x in this terms column, I have to include z in the answer in order for all of these min terms to be used. As well as, how about x complement, y complement? Well, it was used only one time here, so I have to include it as well. So my answer, simplified, is going to be this whole thing reduces to the sum of these candidates, z plus x complement, y complement. And let's look at another example.